Welcome to the short course series hosted by the Packaging Research Center. My name is Madhavan Swaminathan. I serve as the director of the PRC. So today we have an excellent speaker from Intel Corporation, uh, Vidya Jayaram, who graduated from Georgia Tech. So she got her master's in material science and engineering from Georgia Tech, and was one of our PRC students. And she got her BTech degree in polymer engineering and technology from the Institute of Chemical Technology in Mumbai, India in 2015. A very brief background about Vidya. She's currently working at Intel Corporation in Chandler, Arizona as a materials technology development engineer. Her work at Intel has been focused on process and material development of capillary underfills, wafer level fan-out packaging, and thermal solutions for advanced packaging. Vidya is an active member of the ECTC Materials and Processing Committee and the chair for Automotive 5G and Next Generation Application session at IMAP's Device Packaging Conference. The title of our presentation is System Level Packaging, Interconnections, Failure Modes, and Reliability. The short course is for a duration of 1.5 hours. And what we'll do is we'll have Q&A sessions as part of this short course so that you can interact with the speaker. So I would advise all of you to post your questions in the chat box. Carol will ask the question and then Vidya can answer the question. So while the presentation is going on, kindly mute your microphone so that the audio quality is good. So with that, Vidya, the floor is yours.
Thank you so much, Professor. So good morning, everyone. I'm really excited to be here and present this talk. And as Professor mentioned, I'm an alumni of Georgia Tech and also a student of PRC. So I'm really excited to be back and interact with all of you. And I hope you find this presentation useful. Thank you. So with that, let me get started. Today, I will be talking about system level packaging with focus on the different failure modes that we see in the interconnections and their reliability. So the main objective would be to understand and introduce what a system level package is. What are the different types of failure modes we see? What are their mechanisms? What is the need to test their reliability? And how do we design for a reliable package moving forward? So the outline is listed here, and I will go a little bit in depth of each of these focus items. I will introduce what a function of an electronic package is. How does that fit in system level packaging? What are the typical applications and use conditions? What the packaging roadmap looks like, and then go into a little bit more detail of what is failure and what are the causes of failure, how do we manage it, and what can be the different guidelines to mitigate this. So with that, let me get started with the function of electronic packaging. So an electronics package has three main steps. You have the silicon chip that is in a wafer form, which is diced and then assembled onto an interposer or a substrate. And that is then assembled onto the final, on the printed circuit board in the final electronic product. So as you can see here, the three steps. So the main function of this electronic package, starting with the obvious one, is the electrical connectivity. So you want to have connectivity and power distribution between various chip circuits and the devices and the components. In addition to that, you also need the electronic package to be able to remove the heat generated by the chip circuits efficiently to have continued performance. And third, for mechanical protection. So you need the electronic package to have the mechanical structure and stability that would allow for manufacturability. You want to protect it from environmental exposure, damage, and also shielding from electromagnetic radiations. So this is the main, three functions of the electronic package. So let's go a little bit deeper into what system level packaging is. As you can see, I've described, a high level process flow from chip fabrication to system level packaging to the OEM assembly where it goes to the final consumer. So we'll focus on system level packaging, which involves the chip and board level packaging. And what the key differences would be. So chip level packaging would be the schematic on the right where the chip is attached to the substrate through interconnections. That's also called as the first level interconnections. This package is then mounted on the printed circuit board, which is also called as the second level interconnections or the board level interconnections. The overall idea for chip and board level interconnections, or the concept is the same, where you want to fan out the connections from the chip all the way to the printed circuit board. However, there are some key differences when it comes to both of these. Typically, the chip level interconnections are tighter in pitch, smaller in size compared to the board level, which is much larger. You have different manufacturing processes because of the size itself in how the chip level interconnections are formed. That can be through plating, jetting, etc. Whereas for the board level interconnections, you would have screen printing, ball drop, etc. In addition to that, you can also have different materials that are used at both the chip and the board level. And that's mainly driven by what kind of manufacturing methods there are, what is the different size requirements, etc. So it's important to comprehend that both the chip and board level interconnections are part of this entire system. There is a lot of work that is done, to understand what kind of challenges are there at the chip level only, or from a package to board level standpoint. But with our packages getting more complex, it is important to look at both the chip and the board level while designing a package, while looking at any challenges, since they're also interdependent. So system level packaging takes a holistic approach in understanding these dependencies with the objective of having the best performance for the entire system. So going into applications and use conditions of these electronic packages. So for the same silicon chip, you can have a wide range of applications. As you can see, it can go into our phones, laptops, automotive, industrial tooling, process control applications, into network communication and also data processing. So you have a wide range of applications that these packages go into, even for the same the same silicon chip. So all of these applications have diverse or different life cycles and use conditions and different degrees of human interaction associated with them. So for example, you would have your phones that you would use for about 2 to 4 years. And you either want the next new iPhone, or the software and the system is evolving so rapidly that we need to keep up with the next generation of phones. On the other hand, if you look at something like automotive, you typically have your cars that you use for 8 to 10 years, and that's something that would have a little more thermal exposure and would require higher reliability depending on what type of electronic package goes into what system in your car, whether it is inside of the car or under the hood, etc. So there are different degrees of human interaction, and it's important to understand that if something fails in the package, what would be the impact of that? And that would be much higher when it came to something like your automotive space. So that's one of the reasons that's driving high reliability requirements. And if you look at something like data processing, compared to your laptop doesn't require as much data processing compared to server farms. So in this case, the amount of data processed is so large, and you need the processing time to be really low. So each of these different segments have varied use cases, which is why it's important to look at a package from a system level approach to understand what is the application and end use, so that you can develop the system around it. If you look at the market projections today and where we stand today, you can see that the trend is on the high, and it's focused on high performance computing, on data processing, consumer electronics. So the cost for high performance computing is going up, while the requirement for consumer electronics cost is going down. So it's important to not only understand the application, but also what the key drivers are for this trend, and what are the costs associated with it. So if you look at the packaging roadmap, talking about what complexities lie ahead, it was a pretty interesting quote that I read in this paper recently, that the time in the microelectronics industry today is an era of hyperscaling. And if you think about it, that's true. We don't have market improvements that are only driven by one type of technology, one type of application. Today we have everything growing all together. You have different market segments, like the ones I mentioned in the previous slide, all growing together. If you see in the past, we had one type of silicon node being used for 4 to 5 years, and then there was enough time for development till we really needed to go to a higher performance package. So today you need something new every year. And if you think about that, to be able to sustain coming up with the next big thing every year, there needs to be significant investment for development. And we are at this inflection point where the annual costs of developing in this era of hyperscaling is going up, and getting much higher than what it used to be in the past. So we have to be extremely cognizant of the cost component, especially looking at what the usage or life cycles for a particular application segment is. In addition to that, we are also increasing the complexities, since we want higher performance in a smaller real estate with lower costs. So we are coming up with all of these cool, complex architectures, and that is increasing the amount of stresses that we see in our system, and that can lead to early failures. So that's also a very important component of a microelectronics package. So with that, let's go into why we see failures. Depending on the type of application that your electronic systems are used in, it's exposed to different types of environment and use conditions. And because of the demand that we see today, and the need for miniaturization and high performance. Sorry, was there a question on the bridge?
Oh, okay. Yeah. So did you book an appointment?
Oh, I think. Can you guys still hear me?
Yeah, I already got invited to the portal and I already set up my account. So, but appointment, I don't see the appointment yet.
Okay, hang on for a second.
No worries.
Can everyone please make sure that they're muted? Thank you so much. Okay, I'm sorry.
No problem. No problem at all.
Wonderful. Thank you so much, man.
Oh, maybe they're not muted.
All right, I think everyone is muted now.
Okay. Yep. Thank you. So as I was saying, the need for miniaturization and high performance is, like we want our phones when we are skydiving, we want our phones when, or we want electronics when we are skydiving or when we are, at the bottom of the ocean. So we can take these pictures and post them on social media immediately. So I think the diversity of the applications are also increasing. And because of that, our electronics packages see a variety of stresses. You would see thermomechanical stresses that are more environment driven, where the package would experience fatigue and creep and warpage induced defects. I'll go a little bit more into the types of failures in the upcoming slides. But this is to understand what kind of stresses that we would see and what the source of the stress would be. You would have electrical stresses coming from the performance, and mechanical from shipping, handling, that it would experience drop, shock, vibration induced defects. So what's important here is, because of these drastic conditions that our packages might experience, failure is something that is inevitable, and it's a part of success. So it's important to learn from them, understand what is causing them, understand the time to failure, and how that can be managed to be able to predict these fails and how we can apply them to our end use case and have it be sustainable and reliable for the time that it's required to be functioning. So it will never be a single point solution. It will always be a unique solution to each problem with all of the interdependent factors. However, the interdependent factors are what is interesting, because understanding and learning about the impact of failure, how it can be managed, what is the impact of cost, how many years does this need to be sustained. The concept is very similar. So with every growing trend, or with every next improvement, it's important to understand all the failures that we have seen so far, so that we understand how we can delay it or manage it for the next improvement. So with managing failure and extending reliability, there are four main, I would say, steps or guidelines to how you would go about assessing the failure and designing for a more reliable system. So the first one would be identifying the failure mode. and how to detect it based on the expected failure modes seen on previous learnings, and developing this sort of risk assessment. Once you have that, then you would go into the next step of failure prediction, where you have tools and resources like modeling to predict the stress locations and what kind of failure modes through input of existing experimental data from previous learnings and extending that to your use case. And then once you have your failure modes identified and you have some understanding of what kind of failure you would predict, you would then move to performing some accelerated stress tests. And you would select these tests based on what you've learned and what the model has predicted so far. Once you have this data, you can then be ready to design for reliability based on your package design, architecture considerations, your material considerations, and your process optimizations. So we'll go a little bit deeper into each one of these steps. So let's start with failure mode identification and detection. So I have listed out in the following slides different types of failure modes that we would see in interconnections at the chip and board level, and understanding where these failures are coming from and what their mechanism is. So starting with solder joint voiding, this is a common failure mode that we see in interconnections. So they can have multiple causes for the same kind of failure mode. So the first one here, you can see voids that are formed during processing. So for example, when you have excess flux that is entrapped, and when this package goes through reflow, the reflow conditions may not be optimum, where it doesn't allow for the volatiles to escape efficiently. So they get trapped inside the solder, and that's how they form the solder voids. This is more of a processing related defect or failure. But another type of void formation can be electromigration induced. So this can happen over time while the product is in use, where it's a current driven diffusion, as you can see in the mechanism here, that's causing these voids. And electromigration can also cause the voids to grow and cause solder cracks or opens. So it's really important to understand when you see a failure, what is causing that. Another type of failure is solder joint cracking. So you can see images here of, again, similar types of failure that are induced by different mechanisms. So looking at a process level mechanism, again, which could be warpage induced, this warpage is typically caused by CTE mismatch. You have a silicon chip that is assembled on, let's say, an organic high CTE substrate. So because of the high CTE mismatch, you would see kind of either a smile shaped or a frown shaped warpage, and that can lead to tensile stress here. For example, where you have a smile shaped warpage, you can have tensile stress at the corner bumps, and that tensile stress can then lead to solder joint cracking. Another type of failure mechanism for this crack is fatigue induced. So this is more of thermomechanical stresses that are experienced by the solder joint. For example, with repeated heating and cooling cycles that can cause high shear strain, again leading to crack initiation and propagation at the weakest interface, which would be between the copper pad and the solder at the IMC interface. And thirdly, you can have solder joint cracking, also because of mechanically induced defects. So if you have like manual handling, storage, where your package gets dropped or experiences some type of shock or vibration, that leads to more brittle cracks compared to the warpage or the fatigue-induced cracks. You would see more brittle cracks, and that would indicate that it's some sort of a mechanical stress-induced damage. And moving to the solder non-wet and open, again, there can be multiple mechanisms. So the first one here is, again, warpage-induced failure, where it's similar to what I mentioned in the previous slide, where because of the high CTE mismatch, you would see either a smile-shaped warpage or a frown-shaped warpage. And for example, for a smile-shaped warpage on the corner, you in the previous case, you had a tensile stress that the bumps experienced because of being stretched, but there can also be cases where the corner bumps don't touch the pads, and that can lead to a non-wet or an open circuit. And in some cases, you have the bump touching the pad, but it hasn't made a good enough contact to actually form a joint. So that can also lead to non-wet. Another interesting mechanism for having a non-wet or open are bake-induced solder opens, and that is also again more thermal stress induced. So at higher temperatures with some level of humidity during bake, this can result in the solder to be consumed. That can basically the free solder gets consumed to form the intermetallics, and that can lead to reduced solder volume in the actual bump and lead to non-wets or opens. Now, this would be a higher risk for reduced solder heights that you typically see at chip level that are more prone to this bulk solder consumption. Another form of failure is solder bridging or shorts. So as you can see, warpage, CTE mismatch induced warpage can cause a lot of defects. So it's really important to look at a failure mode and understand what mechanism it is so that it can be managed accordingly. So in this case, the warpage induced failure with the same kind of smiley shaped warpage where the corner bumps would see non-wet, open, or solder crack. At the same time, you would have the center bumps in this case, for example, that are squished. And because of the large solder volumes typically at board level, these squished bumps would bridge and form a short. Another thermomechanically induced stress that leads to solder bridging could be if there are voids in the capillary underfill that is present between the solder joints. This can cause the solder to extrude into the void when it experiences a thermomechanical stress or repeated heating and cooling, for example. So the solder can extrude into the voids, and that can also lead to bump bridging. So I think before we go into failure detection, I wanted to check Carol, if we wanted to pause for questions so far.
Yes, if this is a good time for you, we can take a question. We do have one in the chat.
Sure.
So are there any established design rules to minimize failures in chip scale and system level packages?
Yes, actually. So that's also part of something I will cover closer towards the end of the presentation. But yes, there are design for reliability guidelines to focus on overall system level reliability, which basically looks at the failure mode, the prediction, the testing, and then designing for reliability. So that's a really good question, and we'll definitely be covering that. And I also have an example listed based on the availability of time for how one of the works that I did at PRC, how I went about using that approach to design for enhanced system level reliability.
Okay, thank you. That was the only question in the chat. Please feel free to unmute yourself and ask a question if you have any right now. If not, we can go on and you can ask at the end of the presentation.
Yep. Thank you, Carol.
Sure.
Okay.
Okay.
So with that, I'll continue. So we have looked at some typical examples of failure modes seen in chip and board level interconnections. So let's look at how we can detect these failure modes so that we are able to study them better, detect them, and then and work towards prediction and improvement. So electrical testing is a quick and relatively common testing method to check for solder joint bridging or open circuits. The good part is a large number of joints can be monitored, and you can help localize the defect area. However, it relies on complete failure or open circuit to be detected, which is around a 10 to 20% increase in resistance to be able to capture these defects. Typical failure modes that you would be able to capture with an open circuit is solder joint crack, voiding, or bridging. So you can see this is a just a manual micrometer schematic of electrical testing measurement. But if you look at the image in the center here, it's typical of what we would use in the industry, where you have the parts in a particular reliability testing chamber that's connected to software that continuously measures the electrical resistance while the package or the system is going through some sort of an reliability testing, since you won't have to actually remove it out of the chamber to come and manually measure it. So that's something that would be more commonly that we would see. And the image here on the right is an example of what this data collection would look like. So you would have some expected resistance, and with more accelerated stress testing, you would see the resistance going up, and you can have different variations of how the resistance goes up. For something that's I would say almost a brittle failure, you would have the resistance rise up immediately, as opposed to a fatigue induced failure, for example, like thermal cycling, where you would see the resistance go up gradually over time and then cross a particular threshold to be detected. And then another type of detection analysis is metallographic microsection. So cross sections are actually very effective in detecting multiple solder joint failures. So this method would involve it's a destructive excuse me, it's a destructive test. So it would involve cutting the samples and then mounting, grinding, and polishing and cleaning and micro etching them to be able to see the cross section of the joint clearly. These joints are then inspected through an optical microscope. This is one of the most common and effective methods to detect or analyze failure. And it can capture most of the failure modes like the joint cracking, voiding, solder joint bridging, non-wets, opens, how does the solder spread look like, post-dipole, shear, etc. So it's an effective method to capture multiple types of defects through cross-sectioning. However, it is a destructive technique. Moving to Xray. Xray is a common technique that's used to detect failures in a non-destructive manner. It can detect damages to internal structures of the package. The main failure modes that are captured through Xray are voiding, bridging, missing solder ball or misalignment of the pumps, as you can see in these images. That Xray, I think, is a pretty effective non-destructive technique to capture these kind of defects. Another technique is scanning acoustic microscopy, or SAM. This is also a non-destructive imaging method to evaluate inner structure failures. It uses two main properties of ultrasound: the fact that sound can be focused and that sound waves reflects at boundaries of different materials. So these are the two main ideas behind using ultrasound to detect failures. So the main failure modes captured here again would be the voids in solder bumps, void in capillary, underfill, or mold encapsulation, like you see in this image here. And it's also very useful in detecting delamination and cracks. So this is another, great non-destructive technique to capture a lot of these failure modes. And typically what we see is we use the non-destructive techniques first to kind of see to check for defects. And if we do see anomalies, then we can go into more destructive testing like cross-sectioning and figuring out what's actually going on to get more information about the failure. And SEM combined with EDX is another very effective method to capture defects. And this method, actually even more so than capturing defects, gives us a lot more insight about what is actually going on. And this can help us figure out what the root cause of that failure was to begin with. So it provides magnifications up to several tens thousands of X, while the depth of field can still be in the millimeter range. So that's one of the differences compared to cross sections, where you would have the optical magnification, whereas SEM has the electron microscopy, like a higher level of magnification. And combined with EDX, it's not just a higher level of magnification, it also provides input about the elemental composition. As you can see here on the bottom right picture, where it can give insight about different atoms, elements, the intermetallics that are formed. So the typical failure modes that you can capture with this would be the solder joint cracks and voids. But more than capturing the failure mode, I think SEM combined with EDX is a very effective tool to understand the root cause of the failure. So with that, we covered, how do we identify different failures and how do we detect them? And having this this knowledge base, I think we can move to how do we predict failure. So for failure prediction, finite element analysis is usually used to predict different types of stresses and reliability performance. It can be used to model for, different thermomechanical stresses, bake, hast induced stresses, but it can also be used to model process level information, like how much warpage we would expect based on the CTE mismatch, etc. So typically it is coupled with empirical models like Coffin-Manson and Engelmeyer, to name a few, to correlate how the stresses can be translated into the predicted time to fail. For example, for thermal cycling reliability, where you subject the samples to cycles of high and low temperatures, it can predict how many cycles to failure based on the input parameters. So it's a very effective tool in predicting what the failure might look like. But before you even go to this sort of predictive modeling, it's important to understand what kind of failure modes that you would expect so that you can model accordingly. Since there's no model without existing empirical data and your input based on the failure mode that you expect. So after you identify a failure mode and detect it, and you're predicting what type of failure to expect, the next step would be to perform accelerated testing based on the model prediction, and you would get to actually see what kind of failures might occur. So the most important part about accelerated testing, or the key consideration for reliability testing, is that it should be able to mimic the use conditions for your product based on what kind of application, what kind of temperature ranges it's going to see, what kind of weather conditions, what kind of use conditions that your package is going to see. It is very critical to have your reliability test be able to mimic that sort of use conditions. So I think what's interesting about performing this kind of stress testing is no matter what the use condition, no matter what the kind of reliability test that you're performing, you would see a similar kind of bathtub curve for the failure rate predicted over a product lifetime. So in the beginning, you would see latent fails or early failures. This could be mostly induced by your process level yield loss. For example, in the beginning, when we spoke about voiding in the solder joint caused by process-induced failure, maybe the reflow conditions were not optimized for the void to escape effectively. These voids that are in the package can grow and lead to an open and early failure, but that's induced because of the processing. So this is something that's needed for every single electronics package, where you want to kind of weed out all the early failures and the latent fails, so that you can focus on what you would expect to be a normal distribution for your process conditions and your fail rate. After that point, you would see the curve stabilizing a little bit, where now that all of the yield related failures are weeded out, the failures are more consistent, where all of the units kind of behave in a similar manner after some long period of operation. After a certain point, we reach the wear out region, where at this point you would see multiple failures occurring for most of the parts that were tested, since this is when your package, based on the process, the material, the architecture system that you have set up, is finally starting to wear out. So this would be a typical bathtub curve fail rate prediction over time that you would see for any kind of reliability testing. And it's really important to understand, what are the yield loss related failures, what are the wear out related failures, and you would also see some random fails that you may or may not have expected, and figuring out what the root cause of that failure is through your mechanism understanding and detection will provide you with learnings that are specific to that particular material set or design or package that can be used to predict the next set of improvements. So with that, let's go to what are the different types of reliability tests. You can have accelerated stress tests, and I know we spoke about it in pockets throughout the presentation so far. You can have temperature cycling, bake, and HAST, and we'll go a little bit more into details about all of these. But the general failure modes that you can detect with these kind of reliability tests are solder joint fatigue, delamination, substrate cracks, die cracks, like voiding, IMC formation, degradation, etc. And you also have another type of stress, that's mechanical stress, that we touched upon, where due to storage, transportation, handling, you would see drop, shock, and vibration kind of stresses, which can help us detect failure modes like cracks and brittle joints, etc. So I think the main, the key message here is there are different types of stress tests available, but the key is to figure out what tests are critical for the failure modes that you would expect, and how do we pick the right one. Or there are many paths to enlightenment, and be sure to take the one with the heart, or the one with the highest fail rate. And I thought that was funny. But I think that's what's critical. Since there are so many tests available, it's important to understand what it is that you are looking for and what test to pick accordingly. There are, the failure mode can be simulated with not just like one test condition, but you can have multiple tests in combination that would be giving you the information that you're looking for. So that's how you would define what kind of reliability test you want to pick. So let's go a little bit deeper into each of those reliability tests. The first one being temperature cycling. This is one of the most common type of stresses that or common type of reliability test that we would use to accelerate different fatigue related failure modes. What it is cycling from a really low temperature to a really high temperature and going in cycles with a specified period of time between these between the high and low temperature cycles. So depending on the use conditions, these three parameters can be varied to simulate the environmental condition that you would expect to see as part of the product use case. Additionally, it can also be used to understand the thermal or thermomechanical stresses that are experienced by the processor itself when you're turning on and off. So those are typically the kind of simulated stress conditions where you have the environmental conditions and also the heat generated by the processor itself. The key failure modes with this, as we discussed, are bump, cracks, substrate cracks, die cracks, and underfill delamination, etc. The image here on the top right, you can see the crack initiating and propagating over a period of time with increased number of thermal cycles. Another really effective stress test is humidity accelerated stress test. So the unique thing about this is, in addition to temperature component, you also add a humidity component to the testing. So the concept is to completely saturate the chamber with moisture and keep it at a high temperature. So variety of HAST tests are available where you have unbiased versus biased HAST, where a biased HAST would also include passing an electrical current through it, which would be more, which is an additional modulator that would maybe simulate what your package is experiencing in a more realistic scenario. But it's more of, what kind of failure mode you're looking for and how that can be captured to pick between biased or unbiased HAST. So this typically will mimic your use condition or stress condition where you have the parts being stored, shipped, or even in use, where you have areas with higher moisture, higher temperatures, etc., that would be able to simulate different kinds of fail modes like delamination and electromigration, etc. The next one is bake. So bake is also called as high temperature storage test. So how bake differs from temperature cycling or HAST is that it goes to much higher temperatures, almost up to 300 degrees Celsius, and typically for a much extended period of time. Bake is interesting because it simulates a it does simulate a thermal stress condition, kind of similar to HAST and thermal cycling. However, it looks closely at the joint quality due to high thermal exposure. So for example, if you want to see over with high temperature and extended period of time, if you want to accelerate the failure of the solder joint, you would see over time the bulk solder gets consumed to form the IMCs, and that's something that would be able to, it'd be able to detect that with a bake type of stress test. So we covered some of the accelerated stress testing. And then you also have mechanical reliability tests to simulate the package being dropped or experiencing some kind of vibration or shock. And we typically follow JEDEC standards to perform this kind of testing. The stress condition that it would most simulate would be transportation, handling, and even at end use where the consumer handles the product and it experiences drop and shock, etc. And as we covered earlier, this would be more brittle type of failure modes. You would see die crack, bump crack, substrate or PCB crack, deformation, etc. These are things you would be able to detect with the mechanical reliability test. And what's also interesting here is if you look at the plot on the top right, you see the mechanical input signal that's been provided to the package, but the response or the experienced shock output is follows a similar curve, but the response is different compared to the input, which tells you that there are so many different materials and process steps involved in having your or assembling and having your final end product, that each of these materials, and because of their processing conditions, react differently to shock, and you would see different kinds of failure modes accordingly. So we've covered the failure mode identification, prediction, and what are the different types of stress testing. And the question that was asked on the bridge earlier is, are there any guidelines on how do we design for reliability? So that would be a very critical step, once you've kind of identified and predicted your failure modes. Based on the learnings that we have so far, how do we design a system? What kind of materials do we pick? What kind of geometry do we pick? What kind of architecture do we pick? So many of these factors that come into play for having the performance that you want, but at the same time designing for enhanced reliability. So going into a little more detail about the design for reliability considerations. You have three main components to it. You have the package architecture, where you would consider, what kind of overall architecture you want to pick. Is it going to be a 2D or a 3D package? Is it going to be, wafer level fan out? Different kinds of architectures that you want to pick. In addition to that, it would also include geometry, what your bump pitch is, what is your die thickness, what your bump and trace layout would look like, or what CTE you want to pick for your substrate based on what CTE mismatch you would expect. So it's a game of balancing performance versus stress. The second consideration is material selection. So depending on the application that it's going to and what kind of reliability you need, you can pick solder alloy materials like doped solders, or you can pick compliant interconnections, again, to balance kind of the performance and the stress aspect of it. In addition to that, you also have substrate interposer materials. Like, do you want a silicon interposer? Do you want an organic interposer, glass interposer, etc.? Again, based on your processability, cost, and CTE matching to reduce the stress. And the third component to design for reliability is process optimization. So you have your architecture selected, you have your materials selected, and now you want to optimize your process to gain the best out of, or most reliable, low defect, high yield process to have a robust package. So for example, your bonding profiles, where you can control the heat, the force, temperature, time, to mitigate warpage, to mitigate bump bridging, non-wets, etc., from a process standpoint, and or even reflow conditions, for example, to manage solder joint voiding. So these are the three main considerations to design for reliability. So with this, I have an example for how, one of the projects that I worked on when I was at Georgia Tech, how we went about this methodology. So Carol, I wanted to do a check again for any questions, and then I can conclude with the examples and the summary.
Okay, we do have a couple of questions in the chat.
Sure.
So the first one is, you mentioned about bake-induced solder crack. What is the main purpose for the baking step?
Okay, I can go back to the slide. Yeah. So the main purpose of the bake-induced failures is to stress it at a much higher temperature than what the package would experience, more to kind of accelerate and simulate how the solder joint would get consumed or how the IMC would be formed over time. And that's one of the most critical fail modes that we capture using bake. Did that answer the question?
We will assume that it answered the question. If it didn't, please let us know. Another question, how do you distinguish the cracks induced during sample preparation for cross sections from the cracks already existing?
Oh, that is a good question. I think one of the key steps in cross-sectioning itself is the sample prep. So we need to be really careful while preparing the sample. However, if there are some level of defects, I think going with the flow that I mentioned on what is the failure mode and how do you detect it, especially if you look at different techniques like optical microscope cross section, SEMEDX, you can kind of fundamentally understand what caused these cracks. So you might have some polishing level of contamination that you might find in the joint that you will be able to capture with the EDX elemental composition. That will give you some idea that, okay, this is probably created by my polishing defect. On the other hand, you also have an understanding at this point of your expected failure modes through prior learnings and also model prediction. So if you do see something that you don't expect, that could also be one of the reasons to look deeper into, is this being caused by a polishing related defect. But I think one of the most effective ways would be the elemental analysis through SEMEDX to kind of give you an idea of that.
Thank you. This question, I'm going to attempt to ask it. Andrew, if I don't convey what you're meaning to say here, please feel free to unmute yourself. So it says, for flip chip underfilled packages, is it generally accepted that HAST and THB testing exercise the same failure modes, or does HAST perhaps introduce new failure modes that might not be representative of field failures?
That is a good question. So I think for TCB and HAST, even though you do have failure modes like crack and delamination that you would see because of fatigue failures, HAST, I think, would add a humidity component to it that you would see during storage that we might miss, in the temperature cycling profile itself. However, having said that, understanding what the application of that part is, to understand what kind of environmental conditions it's going to experience, and even deciding, what the temperature range and the humidity levels should be, will help to accurately estimate what the fails will be, as opposed to inducing additional failures with just the stress test itself. So that's why it's very critical to design your reliability test based on the use conditions, to mimic the use conditions.
Actually, just to add to that question that you read just fine, but I was more asking between a HAST test that's like at a 130 C and high pressure versus a THB test at maybe 85 that you need to run longer, but perhaps the worry would be when you're doing 130 C high pressure, that might induce, I don't know, swelling failures, things like that, that might not be representative of a THP test that might actually pass it.
Yes, yes, that's true, which is why a lot of times these tests are done in combination. So for a part that is um, going for a certain set of applications, you would put some of the parts for temperature cycling and some parts for HAST. So that way, at the end of the day, no matter the results that we get from these tests, it's up to our understanding to be able to detect, what would be expected of this kind of use condition versus not. And especially when you have both data sets from temperature cycling and HAST, you would be able to kind of weed out anything that you think is caused specifically by the accelerated test itself. So a lot of times we do multiple tests in conjunction to understand our failure modes.
Okay, thank you. Andrew, you also have another question. Do you want to go ahead and ask that about the high temperature storage testing?
Sure. So high temperature storage tests is, causes the growth of IMCs, as you showed, and that increases the resistance. And I'm thinking here of the case of copper pillars that have relatively thin solder. What can be done to limit that change in resistance? Are there barrier metal layers that you might want to have in there? And is it perhaps better to have a very thin solder joint so the whole joint becomes IMC? Is that maybe better to make it resistance to changes in resistance by high temperature storage?
That's a good question. I think we do have different types of soldered joint or formulations based on what our use condition might be. But for something like high temperature storage, you would still, it's still not ideal to have a full IMC joint or a very thin layer of solder, since that can lead to brittle cracks. But it depends on what kind of mechanical stresses or even fatigue stresses that package is going to experience, in addition to just the high temperature storage. So even if you do have solder that's getting consumed, the key here is to understand two things. One is, when it does get consumed to form these IMCs, what are the different types of IMCs that are formed, and what is the nature of those IMCs? You can get that through phase diagrams, etc. And the second is, what is the time to fail? So even if I do have these, the free solder getting consumed to form the IMCs, am I able to sustain for the time period or the use condition and application that's required? So it's a good tool to understand what's happening, and at the same time, consumption to form IMC is not always bad. It's important to understand the mechanism and have it last for as long as you need it to be.
Thank you for that.
Thank you.
Thank you. So we have a couple more questions. The first one, can you explain more on the biased HAST? As the name suggests, is it like biased voltage supply? For what applications would you prefer biased HAST over HAST?
Okay, so yes, biased HAST is where you do have electrical voltage that's applied in addition to the temperature and the humidity. Typically, we use unbiased HAST in conditions to simulate, storage, shipment, etc. Where we would be able to capture interfacial delamination of the underfill, passivation, mold, etc. You would use biased HAST to simulate a functional part, because your part in use will be, in function, experiencing this kind of current flow and electrical voltage. So bias test would be more representative of not just storage and shipment, but also the part actually being used. However, to be able to test bias test, you need to you need to have separate test vehicles for that with test structures to be able to test the electrically test the bias test. So it depends on it's more of, you know, what kind of test you want to select based on what risk level you see for a particular failure mode. So bias test is something that would be more you know, time intensive and more intensive in terms of preparing these test vehicles to test to begin with, whereas unbiased test does not require that. So it's a trade-off between how accurately you want to simulate a functional part that's in use in addition to storage and shipment versus evaluating the risk of storage and shipment itself, for example.
Thank you. And the final question, for now at least, what are the differences for SJR failure between chip level interconnect versus board level connection? For example, which specific areas are impacted due to warpage and thermal cycle?
Yes. So for chip level versus board level, they're both at the end of the day, you know, interconnections with a similar purpose, but they have different manufacturing steps. So you would see things like underfill delamination, passivation delamination, die cracks, things like that, more on a chip level. As opposed to on a board level, since you don't typically have underfills to mitigate the stresses. So most of the stress is concentrated on the board level interconnection itself. So there are differences in terms of, you know, what kind of failures you would see. But at the end of the day, we still want to protect our joints, and some of the failures that we would see with, you know, cracking and voiding, etc., would be of a similar fashion. When you talk about warpage induced defects, if you have, let me find the slide for that. Yeah. So when you talk about warpage induced defects, you have a tighter, you know, chip gap at chip gap height at the chip level compared to the board level. So there is a higher likelihood that you will make the connection with some level of warpage at the chip level, which would be higher risk at a board level, where your sizes are larger, the pitches are larger. So you would see warpage related failure modes more on the board level interconnection side, with solder bumps bridging and you know, warpage related non-wet. So the same type of failures can happen at chip level, and they could be a different mechanism or of a different intensity. For example, if you didn't have good alignment while doing your chip level assembly, since the pitches are so much tighter that you could easily have a misalignment, for example, that could lead to missing solder or missing bump connection or bridging, things like that. So what's important is to understand, if this is my failure mode, what are the different mechanisms that it could be caused by? And that would also be related to what kind of process steps we have at chip level versus board level.
Okay, that was the last question, so you can
Okay.
continue. Thank you.
Thank you. So let me go to the example. I thought that might be an interesting way to kind of end the talk. Doesn't allow me to go to the link without, yeah. Okay. So one of my projects, at Georgia Tech PRC was to enhance exactly the system level reliability for a 2.5D class VGA package. And we followed a kind of similar structure to identify the failure mode, predict it, do some sort of stress testing, and finally design a system for reliability. So the first step in terms of identification and detection was to perform a risk assessment of what the expected failure modes would be based on previous learnings. So here we basically identified two main risk areas. One is fatigue related bump cracks, where we, based on the prior work done at the lab itself, we saw failure for failure at the BGA bump, closer to the substrate and bulk solder interface, for a low CTE glass, and we saw how that failure propagated to the lower end by using some sort of strain relief mechanism like a polymer collar. And this is less likely to fail compared to the one on the top. So that's how the board level reliability was extended. So that was one learning. And the other one was warpage related or warpage induced defect, where we saw that it was critical to optimize your process conditions to get the minimum warpage as minimum as possible during processing, so that you don't induce additional failure modes. So here the warpage was dependent on the thermal cycling bonding, thermal compression bonding, sorry, at the chip level by changing the temperature profile that was used. So these were the two key failure modes that were identified. And then we developed a model around it to predict what kind of failures we might see, and if that's similar to the learnings that we've had in the past. So we modeled for warpage and we modeled for thermomechanical stresses. The warpage modeling had a couple of components to it. We modeled the warpage with different CTE of the glass interposer, and saw how the warpage was modulated, or how the room temperature warpage was modulated accordingly. And this was at chip level assembly, and we also looked at after board level assembly, since it's critical to look at both, because something that impacts at chip level might have a worse effect on board level assembly. So board level, since our printed circuit boards are high CTE, overall the trend or the intensity of the change in warpage was lower compared to chip level, since there is a lower CTE mismatch here compared to chip level. But we saw a trend where with increasing the CTE, the warpage was reduced. And then for a BGA model or a thermomechanical stress prediction, we modeled, we had a 2.5D design, and so we had a 2.5D model design, and we subjected it to thermal cycling stress to see where on the joints or where in the package would be the high stress locations. So the high stress locations were at the corners of the chip and board level interconnections. The next part was to run some accelerated stress tests to understand, what kind of failures we see. And some of these images, I had used to even explain the different types of failure modes and mechanisms. So we did see two types of failures. We saw process-induced failure, where because of high warpage at chip level, we did not have good contact of the corner bumps to the copper pad. And We also saw fatigue-related failure mode, where stressing it with thermal cycling test over time led to solder crack at the IMC bulk solder interface, which was the weakest point. Now, at this point, we had to design a system to extend our system level reliability, considering the chip level defects and the board level defects. So we use the approach for package architecture, material selection, and process control. So the first part was to model this 2.5D system to check for chip and board level fatigue life as a function of the glass CTE. So we used the property of glass with tailorable CTE to kind of check for what CTE would be optimum to have a chip level as well as a board level reliability, balanced reliability rather, since they're both going in opposite directions. So overall, I think that model was really helpful in figuring out what kind of strain relief mechanisms we want to use. So for example, in the prior learnings, we saw that having polymer collars around the BGA changed the location of the crack from the top of the bump to the bottom. And in addition to that, in terms of the material selection, so in terms of using polymer collar, we also used doped solder. It was a manganese doped solder. And we tested that with and without polymer collars to check for the reliability performance compared to what was done in the past. And lastly, we used our process condition understanding to minimize the warpage. So we modeled for warpage for different glass CTEs, and we saw interesting results from the model where the direction of warpage changes from negative to positive, or a smile shape to a frown shape warpage with different temperature conditions. And the fact that it went from negative to positive meant that there is a point of net zero warpage that can be achieved by tweaking the temperatures. So these were critical learnings in terms of modeling for the fatigue life, understanding what kind of materials we would want to use, and picking our process conditions to get the minimum or the least warpage possible, so that we don't see any early failures or the latent failures caused due to process and yield. And at the same time, use these advanced materials or strain relief mechanisms to extend our reliability. So I think that was a good example in terms of how we went about dealing with failure, managing it, and extending our reliability accordingly. And when I joined, and initially, when this is the project, that I wanted to work on, I was wondering, I was kind of not feeling good about the fact that, there are some failures while processing. But towards the end of, this project, I was rooting for failure. I was excited when I saw a failure so that I could go and run all of these detection analysis methods to figure out why the failure occurred. Because if something doesn't fail, then you don't quite understand all the stresses that your package is experiencing. So the one thing that I definitely took from my time at Georgia Tech is that failure is critical, failure is inevitable, failure is fun. So in summary, I think it's important to comprehend system level reliability as our packages trend towards higher performance and complex architectures. And as I said, failure is inevitable, and how we manage it is critical based on the kind of application and end use. And it is important to optimize the fail rate, but also keeping in mind the development costs and the application requirements. So we need to look at it from a systematic approach standpoint to identify and predict failure and extend reliability. So thank you. That was my talk for today. Do you all have any questions, any comments?